Welcome! In this lesson, we build an intuitive picture for local membrane curvature generation and spontaneous curvature. We will see how flexible polymers, adhesive nanoparticles, and membrane-binding proteins bend membranes locally, and how many such local events add up to a preferred or spontaneous curvature. First, a convention. We take the exterior aqueous compartment to be above the membrane and the interior to be below. A membrane segment has positive mean curvature when it bulges upward toward the exterior and negative mean curvature when it bulges downward toward the interior. The energetic preference involves the square of the difference between the actual mean curvature and the spontaneous curvature. Local curvature from an anchored, flexible polymer. Imagine a polymer tethered to one side of a flat membrane. The polymer wants configurational freedom. It gains entropy if the membrane curves away from it, creating extra space to explore. This entropic push bends the membrane away from the polymer. A rigid, adhesive nanoparticle partially engulfed by the membrane directly imposes its surface curvature. If the particle is much larger than the membrane thickness, the membrane wraps and locally matches the particle's curvature. Even very small adhesive solutes, with sizes below 1 nanometer, can generate large, spontaneous curvatures. Simulations showed they increase molecular area per lipid on one leaflet, producing curvatures as large as 1 over 20 nanometers. The opposite sign can arise when head groups condense, for example, when calcium binds to negatively charged membranes. Membrane-binding proteins often behave like non-spherical Janus-like nanoparticles, rigid, banana-shaped, and patterned with adhesive and non-adhesive surface domains. Two mechanisms can operate. If a planar membrane can bind some adhesive patches, the protein induces curvature by an induced fit. If those adhesive patches are only reachable by a curved membrane, the protein senses and stabilizes existing curvature, a conformational selection. Many local benders sprinkled over the membrane add up to a spontaneous curvature. A simple expression is m equals a 1 times m 1 times parentheses phi x minus phi in parentheses. Here, m1 is the local mean curvature field generated by one particle on an otherwise flat membrane, integrated over its affected patch of area A1. The coverages phi x and phi in are the numbers of bound particles per area on the outer and inner leaflets. When outer exceeds inner, m acquires the sign of the single particle curvature. The spontaneous curvature spans an enormous range, from the inverse size of giant vesicles, about 1 over 50 micrometers, all the way up to about 1 over 20 nanometers for strongly decorated membranes. A short history. Preferred curvature was discussed for surfactant monolayers by Bancroft and as a splay term by Frank in liquid crystals. For lipid bilayers, Helfrich introduced spontaneous curvature in the bending energy. With constrained leaflet areas, Evans and later Svetina and Zex developed the bilayer coupling idea, generalized into the area difference elasticity model by Wortes and co-workers. In many nanotube and particle engulfment settings, large local spontaneous curvature dominates, and area difference elasticity adds only a small correction. Finally, the sign. The preferred sign of m is the sign of the curvature that lowers the elastic energy. Because the energy density goes like parentheses m minus m parentheses squared, the membrane tends to adopt m equal to m. With the exterior on top, m positive prefers upward bulges, and m negative prefers downward bulges. Putting it all together, a polymer brush on the exterior pushes the membrane away and tends to favor negative curvature. A large adhesive particle or banana-shaped protein on the exterior can impose or prefer positive curvature. Many such local benders on the two leaflets combine through their coverages into a net spontaneous curvature, m. Summary. Local generators from polymers and nanoparticles to curvature-sensitive proteins bend membranes by entropy, geometry, and adhesion. Their imbalance across the two leaflets sets the spontaneous curvature m, and the membrane then relaxes toward m equal to m by minimizing the bending energy,